Hello and welcome to Sleepy Scientist Stories. I'm so happy you found your way here. Whether you're lying comfortably in bed, relaxing on the couch, or letting your thoughts drift as sleep gently approaches, this space is meant just for you, tonight. We'll take a quiet journey into something mysterious, beautiful, and hidden from everyday life. Beneath the surface lies a 125-year-old physics problem. A story about how a simple question about light led to a discovery that transformed our understanding of reality. I should mention, I've tried to make this video as calm and soothing as possible. But there's always a small chance it might be just interesting enough to keep your mind awake a bit longer. If that happens, at least you'll drift off a little more curious and wise. If you're enjoying this calm moment, I'd truly appreciate if you gave this video a gentle like and perhaps subscribed for more cozy science journeys like this. It really helps sleepy minds like yours find their way here. And if you feel like sharing, let me know in the comments where you're listening from and what time it is there. I love seeing this constellation of bedtime lights spread around the world. As always, this video is made purely for relaxation, comfort, and educational curiosity. It's not meant as medical advice or a replacement for sleep therapy. Tonight, we don't begin with answers, but with a question, a problem that quietly lingered in the universe for over a century. Patiently waiting for curious minds to notice, there's something comforting in how the universe surrounds you, a vast, dark ocean stretching far beyond sight, sprinkled with the gentle glow of distant stars, like tiny lanterns scattered across an endless velvet sky. As you lie here, breathing slowly, sinking into the surface beneath you, the universe feels close, as if leaning in to share a soft whisper, a quiet story waiting to unfold. Tonight, there is no rush toward answers. You're simply drifting into the edges of a mystery, a puzzle that hums beneath reality itself. This puzzle has lingered for more than 100 years, patiently waiting for someone to pay attention. It's the kind of problem that hides in plain sight, appearing simple yet so stubborn that even the greatest thinkers of a generation found it frustrating. This story doesn't begin with distant galaxies or collapsing stars, but with something far more familiar and humble: light. The gentle glow of warmth, the flicker of a flame, the bright radiance of the sun. In the late 19th century, scientists studying how objects glow when heated noticed something strange. When metal is heated, it glows red, then orange, white, and finally blue. You've seen this yourself, in the embers of a fire or the glowing coils of an old stove. It seems simple and predictable. But when scientists tried to describe this glow with math, the equations failed, according to physics. At the time, the energy given off at higher frequencies, like ultraviolet light, should keep increasing without limit. It suggested objects should release infinite energy at these frequencies, which, of course, they don't in reality. The world doesn't erupt in invisible flames every time something is heated. This problem became known as the ultraviolet catastrophe, a dramatic yet poetic name. It wasn't a catastrophe for the physical world, but for the mathematical models scientists had built so carefully over centuries. The universe seemed to quietly refuse to fit into those tidy frameworks. Nature was whispering a subtle truth, just beyond reach, like a dream fading before you can grasp it fully. The question remained, why didn't the models work? Why did the light behave so differently? This wasn't a small curiosity. It touched on the very foundations of physics, how heat turns into light, how energy moves, how the smallest pieces of reality interact beneath everything you see and touch. This puzzle waited quietly. Scientists at the time valued precision and logic. They had built a worldview filled with certainty, with clocks, levers, and gears, a universe ticking like a giant mechanical watch. But now, that watch had stalled, stuck on something it couldn't explain, something hidden in the glow of heated matter, softly whispering from the core of reality. The solution wasn't yet visible. But the question had been truly noticed. And that noticing was the beginning of something much bigger. Tonight, as you lie there, breathing slowly, you step into this story. Not as an observer, but as someone gently following the same path those thinkers once explored. your mind drifting through the same wonder and quiet confusion. Imagine the room where it began. A small laboratory in the late 1800s. The air smells faintly of oil lamps and metal. Brass instruments glint, lie scattered, ink stains fingertips. Someone sits at a desk, looking inward, not outward, at the strange behavior of a simple glow, something that should have been easy to explain, but refused to be. You can almost hear the faint scratching of a pen, the ticking of a clock, the silence between thoughts, as if the universe itself is holding its breath, waiting for a quiet shift. Not a sudden burst, but a subtle turning of a page, a whisper becoming a clear voice. The ultraviolet catastrophe wasn't just a mathematical failure. It was a sign, a doorway hinting that the world was far stranger than it appeared. As you drift gently through this moment, you feel the edges of certainty soften. You realize that the universe is both knowable and deeply mysterious, both close and beyond reach. The glow of heated matter becomes more than light. It becomes a clue, a question wrapped in radiance, waiting for someone to ask, why? Why does this happen? Why does the math fail? What secret is hiding inside the glow? As your thoughts drift softly, like clouds on a gentle breeze, you realize every great discovery begins like this. You drift now through the folds of time, back to a world that felt slower, simpler. A world of gas lamps on cobbled streets, pocket watches ticking steadily, and scientists convinced they were close to knowing everything. As you float unseen through lecture halls and quiet labs of the late 1800s, you sense a unique confidence. In the air, a belief that nature was almost fully explained. The universe felt like a grand clock, each part fitting neatly into equations. From swinging pendulums to orbiting planets and rising tides, everything seemed understood. But underneath that sense of completion, something waited, subtle and restless, a quiet trembling beneath certainty. It started with something simple. The glow of heat? You've seen it many times. The way iron glows red when heated, or a stove coil turning orange then white. To scientists then, this glow wasn't just a curiosity. It was a window into the deep workings of nature. How matter stores energy, how heat turns into light. They believed the answers were within reach, guided by classical physics and the elegant math of Newton and Maxwell. Yet the closer they looked, the more this heated glow slipped away from their expectations. They began describing it mathematically, imagining an idealized object, a black body. Something that absorbs and emits all radiation perfectly, a theoretical construct known as a black body, simple in concept but incredibly powerful in its applications. Through this idea, scientists hope to describe how light emerges from matter at different temperatures and colors, yet when they performed the calculations, the equations began to unravel. At lower frequencies, their predictions matched reality quite well. But as frequencies increased toward the ultraviolet, the math collapsed. Predicted energy skyrocketed toward infinity, suggesting that even ordinary objects should emit endless amounts of high-frequency radiation, essentially, an impossible burst of invisible ultraviolet fire. Clearly, this does not happen. The world around us does not glow with lethal ultraviolet light. Nature rejects this absurd conclusion effortlessly. This paradox, called the ultraviolet catastrophe, was quietly devastating. It marked a deep flaw in the beautiful framework of classical physics, a subtle indication that something fundamental was wrong at its core. As you drift through this story, you can almost sense the frustration of the physicists, their desks crowded with scribbled papers, ink-stained fingers adjusting brass instruments, checking numbers again and again, yet the universe would not yield. They tried patching the formulas, adding corrections and adjustments, hoping to tame the runaway predictions. But the problem remained, a stubborn knot in reality refusing to come undone. It was more than a mathematical inconvenience. It posed a profound question about how nature truly behaves. It hinted at something deeper. Was reality truly smooth and continuous? Or was there something hidden, something discreet, flickering beneath the surface like grains in a beam of light? This question hovered silently in many minds. but not everyone was ready to face it. The idea that energy might not be infinitely divisible felt alien and unsettling, like standing on the edge of an unknown landscape, looking down into unmapped territory. Yet the glow of heated objects continued to defy neat explanations. The longer they observed, the more obvious it became. The old rules couldn't account for this. The universe was signaling something quietly profound, that the classical picture of a smooth, predictable continuum was incomplete. Like a painting missing half its colors, invisible to the eye but deeply real, you might sense the weight of this realization resting in the minds of those scientists, the creeping awareness that a true answer might demand leaving behind the comfort of centuries-old traditions. As if nature herself was gently inviting them to step beyond the familiar and listen more closely to her soft whispers, not in loud declarations, but in the steady, persistent glow of heated matter. Even as frustration built among some, a quiet sense of wonder began to awaken among others. Perhaps nature wasn't broken. Perhaps the rules themselves were only part of the story, a fragment of a larger, deeper truth waiting just beyond the edge of understanding. And as you continue drifting through this moment of confusion and discovery, your thoughts might begin to circle around a name, a quiet figure sitting alone in his study, thinking and sketching ideas he does not yet realize will reshape the world. A figure whose careful courage would soon unlock a key to this puzzle. Someone about to propose something radical. That energy doesn't flow continuously like water, but arrives in small, discrete packets, like grains of sand. A thought so strange, yet so necessary that it would mark the birth of a completely new way of seeing reality. As this idea lingers in the air, you feel the gentle pull toward the next chapter, the moment when the problem meets its first glimmer of an answer in the hands of a man named Max Planck. Now you find yourself drifting deeper into the very core of this puzzle, as if the universe itself has quietly opened a doorway into one of its most subtle secrets. A mystery that does not shout but hums softly just beneath the surface, waiting for curious minds to notice. It all begins with something simple and familiar, the gentle glow of heat. You've seen it countless times, the warmth of a candle, the orange shimmer of heated iron, the soft glow of a sunset. Yet hidden within that glow is a question so persistent and quietly perplexing that it would force physics to transform in ways no one yet imagined. Here you hover near the concept scientists call blackbody radiation. A curious name for something that touches almost everything in existence. Imagine for a moment an object that absorbs all light falling upon it, every color, every wavelength, reflecting nothing back. This is a black body, perfectly dark when cold, yet glowing beautifully when heated. When it glows, it doesn't shine in a single color, but in a smooth blend that shifts as the temperature rises. First a faint red, then brighter orange, then white, and eventually blue. The color of heat itself changes with temperature, a process that feels natural and intuitive. But as the scientists in the late 19th century tried to describe this glowing mathematically, but their calculations defied them. Early equations predicted that as light's frequency increased, especially toward the ultraviolet, the emitted energy would grow without limit. The math suggested it should rise infinitely, implying that even a simple warm object, like a glowing ember or a heated stone, would release an impossible flood of ultraviolet light, an invisible energy so intense it would burn everything around it. Yet this does not happen. Reality quietly rejects this prediction. It is as if nature looks at these flawed calculations and gently corrects them, saying, "No, not like that. The equations weren't completely wrong." At low frequencies, they worked well, explaining the red and orange hues of cooler objects. But as frequencies climbed toward violet and beyond, the math broke down completely, shattering like glass. This failure became known as the ultraviolet catastrophe. Not a catastrophe for nature, but for the physicists' confidence in their neat models, which could no longer capture what they were observing. You can imagine standing beside them in the dim glow of their labs, watching them scribble equations on chalkboards, trying again and again to bring order to chaos. Their minds were sharp and disciplined, Yet the more they patched the formulas, the more the numbers resisted, almost mocking their efforts. This failure wasn't only mathematical, it challenged a core belief that reality could be understood through smooth, continuous functions, and that energy flowed endlessly and could be divided without limit. But the glowing black body hinted at a different reality. Perhaps nature did not divide itself endlessly. Perhaps beneath the surface there were tiny steps, small grains, like sand under calm water. This idea, though not yet clearly formed, hovered at the edge of their thoughts. They felt its presence, even if they couldn't yet define it, a quiet push urging them to let go of old assumptions and step into something new. But what could this new idea be? Was energy truly broken into discrete pieces instead of flowing continuously? Was light itself hiding a deeper secret? You move with these questions now, feeling their weight not as a burden, but as an invitation to curiosity. A chance to imagine that the world is always more mysterious than it appears. As you linger in this moment of confusion and possibility, a name begins to form in your mind. Not yet a solution, but someone approaching, ready to change everything. A man, quietly working, unaware that he stands at the edge of a scientific revolution. Max Planck. Now you drift toward Planck, a man not drawn to bold speculation, but devoted to order, certainty, and the elegance of classical physics. You find yourself in the soft lamplight of his study, where shelves are lined with books, papers stacked neatly, and a clock ticks steadily, marking each passing thought. Planck believed deeply in a continuous, predictable nature, reality that behaves smoothly like a gentle hill or a flowing wave. Yet here he sits, brow furrowed, pen paused, staring at numbers that refuse to align. The ultraviolet catastrophe haunts him, this strange misbehavior of heated light, this quiet rebellion against established rules. He does not want to change the laws of physics. But the problem persists. Almost reluctantly, Planck begins searching for a mathematical solution, not a new theory or worldview, just a tool to fix the equations and tame the predictions of infinite energy. He imagines something unusual. What if energy isn't infinitely divisible? What if it comes in small, discrete packets that cannot be divided further? He does not believe this reflects reality. He considers it only a mathematical convenience to bridge the gap. He assigns each light frequency a minimum energy, a small packet, a quantum. With this adjustment, the equations finally settle. They match experimental data with surprising accuracy. The runaway predictions vanish. Replaced by a curve that matches the real world almost perfectly, Planck sits back, quietly reflecting on the simplicity of it. Yet discomfort grows. What has he done? Energy was supposed to flow like water or air, not jump in steps like a ticking clock. But the numbers are undeniable. The solution fits far better than any previous attempt. You watch this shift unfold, not in a moment of triumph, but in quiet tension as Planck grapples with his own disbelief. Caught between the safety of the old and the hint of something entirely new, he cautiously publishes his findings, presenting them as a mathematical fix rather than a radical idea. Yet beneath this caution, a deeper idea begins to take root. Energy is quantized. Nature, at its core, might not be a smooth canvas, but a mosaic of countless tiny pieces. Planck doesn't see the full impact yet. To him, it feels like a necessary compromise, not a discovery of fundamental truth. But this idea is like a seed, planted quietly in physics, ready to grow into something vast and transformative. As you float in this moment, you sense the minds of others beginning to stir, thinkers who will take this seed and nurture it further. Minds that will wonder if light behaves as particles, if matter itself might shift between wave and particle, if reality is woven not from certainty, but from probabilities and possibilities, things that are both true and not true until observed. As this thought lingers, you drift toward the next voice in this story. Someone who will take Planck's hesitant step and turn it into a bold stride. A name now softly forming at the edge of your thoughts. Albert Einstein. You drift into a world that feels quietly unfamiliar yet strangely captivating. A world where the smooth fabric of reality begins to shimmer, like reflections on rippling water. Lines once thought clear begin to dissolve, replaced by a grainy, textured, and mysterious landscape. You are floating in the space between certainty and possibility, where the universe no longer speaks in absolutes. But in soft probabilities, the idea that began with a cautious step now starts to expand. Energy, it seems, doesn't flow like a continuous stream, but arrives in tiny, discrete packets, each one a quantum, a fundamental grain of energy. Listening carefully, you realize this graininess extends beyond heat and light. It reaches into the very foundation of existence. Imagine light, once thought to be a smooth wave traveling endlessly, now also acting as a particle, a packet of energy called a photon. Not a continuous glow, but a sequence of precise, discrete steps. You drift into the thoughts of Albert Einstein, a young man quietly reflecting on the nature of light, ready to move beyond classical thinking. Einstein proposes that light is not just a wave, as Maxwell described, but also a particle, a quantum of light delivering energy in precise packets. This bold proposal explains the photoelectric effect, a puzzling phenomenon where light striking metal releases electrons, but only if the light's frequency is high enough. No matter how intense low-frequency light is, it cannot free an electron. But a single high-frequency photon can. Einstein's insight confirms something quietly revolutionary. That energy transfer itself is quantized, bound by the granular structure of the quantum world. And with this understanding, the mystery deepens. If light behaves this way, what about matter? Does the graininess stop at energy, or does it reach into atoms, into the very particles that make up your body and your thoughts? You float now through the quiet work of other physicists exploring these questions. They study atoms closely, wondering if quantum rules also govern matter. As you move through this haze of curiosity, you begin to feel the strange duality at the heart of this new reality. Matter sometimes behaves like a particle, a small, solid piece moving through space. And yet, matter also behaves like a wave, spreading out softly, uncertain, not fixed to one exact place, but shimmering through probabilities. This marks the birth of wave-particle duality, a quiet yet profound realization that the universe does not ask whether something is a wave or a particle. Instead, it softly answers yes to both, depending entirely on how it is observed. Even the word observe carries weight here, a subtle, hidden power. In the quantum world, to observe is not simply to look, but to participate, to influence, to collapse the cloud of possibilities into one specific reality. The universe, it seems, does not fully reveal itself until it is questioned, and even then it responds not with certainty, but with gentle probabilities like rolling cosmic dice. You may feel yourself drifting among these possibilities now, sensing the soft rhythm of uncertainty, the pulse of a universe that no longer promises strict precision, but instead offers patterns of likelihood, graceful clouds of potential rather than fixed points and paths. This is no longer Newton's universe, not the grand clockwork of gears and springs. It is something softer, stranger, more alive in its unpredictability. And yet, within this strangeness, there lies a deep elegance and quiet beauty. In the graininess of the quantum world, the universe becomes not simpler, but richer and more textured, like a painting that reveals new details. Depending on how you choose to look at it. As you breathe slowly, letting this idea settle, you begin to sense that the mystery goes even deeper. For if energy acts like particles and particles act like waves, what laws govern this strange reality? What are the limits of what can be known? And what happens when we try to measure this world too precisely? What slips away when we reach too far for certainty? With this question gently echoing in your mind, you drift toward the next chapter, where uncertainty is not just an inconvenience but a fundamental truth, a principle woven into the fabric of existence, a place where the more precisely you know one thing, the less you can know another, where nature holds its secrets, not out of cruelty, but as an invitation to wonder. You now drift toward another mind, humming quietly. A young man sits alone with an open notebook, his thoughts swirling like soft clouds. This is Albert Einstein, not yet the world-famous icon with wild hair, but a quiet thinker working in a patent office. While reviewing the inventions of others by day, his mind drifts far beyond that small room. Into the very structure of reality, you hover beside him now, feeling the gentle weight of his questions as he considers the strange new rule Max Planck suggested, that energy does not flow continuously, but arrives in tiny, discrete packets, quanta. This idea lingers in Einstein's mind, not as a curiosity, but as something deeper. He wonders if Planck's solution to one specific problem might actually reveal how nature truly behaves. His gaze turns toward light, perhaps the most familiar yet most puzzling of all phenomena. For centuries, light was understood as a wave, a smooth ripple through the electromagnetic field, elegant and continuous. But as Einstein examines the photoelectric effect, a puzzling phenomenon that defies wave theory alone, a new idea begins to take shape. He imagines light not as an endless wave, but as a stream of small packets, each carrying a set amount of energy, photons. He proposes that light consists of these individual energy packets, not just as a metaphor, but as a physical reality. Light behaves both as a wave and as a particle, depending on how we observe it. This radical idea explains the photoelectric effect perfectly. When light of a certain frequency shines on a metal surface, electrons are ejected, but only if the frequency is high enough. No matter how intense low-frequency light is, it cannot release an electron. Yet, a single photon with sufficient energy can dot. It is not the brightness that matters, but the frequency, the energy per photon. As you float beside Einstein's unfolding realization, you can feel the quiet beauty in it. The way the pieces softly click into place, a long-standing puzzle finally yielding to a subtle shift in perspective. Light is not only a wave, it is also a particle, a dual nature hidden beneath the comforting assumptions of classical physics. Another small crack appears in the old worldview. The smooth certainty of the past begins to dissolve into something more mysterious and layered. The universe starts to appear less like a smooth ocean and more like a field of gentle rain, each drop a photon, each ripple a wave. Both descriptions true depending on perspective. Yet, this understanding does not create confusion but instead deepens our sense of wonder. It reveals that the world is not less orderly but more subtly beautiful. Einstein publishes this idea, cautiously yet firmly, knowing it will challenge many. But experiments confirm his view. The photoelectric effect behaves exactly as though light were made of particles. This insight eventually earns him the Nobel Prize. Not for relativity, as many assume, but for this very work. A quiet bridge between the world of waves and the world of particles. You drift now through echoes of this transformation, sensing how physics begins to shift softly beneath your feet. The certainty of classical physics dissolves into a landscape where duality reigns, where things can be both wave and particle, presence and probability. As this revelation settles, a deeper question emerges. If light behaves this way, if energy is quantized, what about matter? Does this duality extend into the atoms themselves? Do electrons, protons, and even molecules follow this strange dance? The answer waits quietly beyond the horizon of thought, like the first glow of dawn hinting at a world yet to be seen. As you breathe slowly, letting this idea deepen, you feel a gentle pull toward the next question, where the universe becomes not just particle or wave, but a tapestry of probabilities, a place where certainty fades into patterns of chance, where the very rules of knowing begin to shift. Where the dance of the quantum truly begins, you drift into a realm where the ground beneath your thoughts softens, where the clear lines of classical physics dissolve into something more mysterious and delicate. Here, the universe reveals itself, not as a mechanical clockwork, but as a shimmering tapestry of possibilities. Particles no longer sit quietly in fixed spots, but hum with a soft rhythm of probability. The question, where is it, becomes not a firm fact, but a gentle cloud of possibilities, hovering in space. Imagine an electron, not as a tiny ball circling the nucleus, but as a diffuse wave, a presence spread out, sometimes here, sometimes there, and sometimes seemingly nowhere specific. This is the heart of quantum mechanics, a theory born not from a wish to discard the old, but from the need to describe what could no longer be ignored. The experiment spoke, the math insisted, and reality itself whispered that at its smallest scales, the world does not act like small billiard balls bouncing predictably, but as something softer and stranger. You now float beside the thinkers who first listened. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, each adding a thread to this evolving fabric. Bohr envisioned electrons not as orbiting smoothly, but jumping between discrete energy levels. Heisenberg realized a fundamental limit. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a flaw of measurement, but a feature of nature itself. Schrödinger proposed another view, describing particles as waves of probability spread through space until observed, collapsing gently into one specific outcome among many. In this quantum world, observation becomes something far more intimate and profound. To observe is not merely to watch, but to participate, to influence, to help shape reality from its swirling sea of potential.